Hey students, this video is going to go over heat stoichiometry. So up until this point, we've done stoichiometry several different times, just plain old regular stoichiometry. We've done solution stoichiometry, we've done gas stoichiometry, so it's no surprise that we can also do heat stoichiometry. So we've already discussed during endothermic and exothermic reactions that heat energy can be either a reactant or a product. So when you calculate your change in enthalpy, your delta H, if that delta H value is positive, that would indicate that it's an endothermic reaction, and so heat would be on the reactant side. If you calculated it, the delta H and the heat enthalpy was negative, that would indicate that the reaction was exothermic, and the heat energy would be written on the product side, like it is in this reaction here. So we would do our stoichiometry the same way we would do any other stoichiometry problems, and use the heat as a reactant or as a product in our conversion factor. So when you see this question here, 890 kilojoules of heat are produced per the amount of each reactant listed. How much energy is produced if 5 liters of oxygen were consumed? Let's pretend that that says at STP. We're not going to do any kind of crazy gas stoichiometry with this too. So that means we always start by writing our given. So we start with our 5.0 liters of oxygen. So since we have liters, we know that there's 22.4 liters of oxygen for every 1 mole of oxygen. And this is where we can use our coefficients, because if we look at our balanced chemical reaction, we can see that for every 2 moles of oxygen, we make 890 kilojoules of energy. So we can put our 2 moles of oxygen down here and our 890 kilojoules of energy up here. And then we can go ahead and solve. So 5 divided by 22.4 times 890 divided by 2. And we would get 99 kilojoules of energy. Sig figs because of our 5.0. Okay, and that's it. So let's look at the next question. 1,049 kilojoules of energy are released when aluminum reacts with hydrochloric acid. So you can see our balanced chemical reaction here. We have our kilojoules of energy as a product because it says that the energy is released. So it tells us how many grams of aluminum are needed when 616 kilojoules of energy are produced. So we start with our given, 616 kilojoules of energy. We put our energy from our reaction down here at the bottom, so 1,049 kilojoules of energy. We're trying to go to aluminum, so we use the coefficient of the aluminum up here, because our reaction tells us that 2 moles of aluminum produces 1,049 kilojoules of energy. We're looking for grams of aluminum though, so then we have our 1 mole of aluminum down here, and we would have 26.98 grams of aluminum up here, which is the molar mass of aluminum. So we have 616 times 2 divided by 1,049 times 26.98. And we would get 3 sig figs, so 31.7 grams of aluminum would be our answer. And then our example 3, in the combustion of C2H6, 3,120 kilojoules of energy are produced. How much energy is produced in the combustion of 21.50 grams of dicarbon hexahydride? So we would start with our given, 21.50 grams of C2H6. Now, what are we going to put at the bottom of our conversion factor here? The molar mass. So we calculate our molar mass. That would be 30.1, and that is equal to 1 mole up here on the top. Once we get it into moles, we go back to our chemical reaction. We use the coefficients. So 2 moles of C2H6 would give us 3,120 kilojoules of energy. Now, it just so happens that all 3 of these examples had a 2 coefficient with the substance that we were either starting with or trying to solve for. So don't assume that it's always going to be a 2 on top of or underneath the energy from the reaction. It's going to be the coefficient for that substance. Okay, so make sure it's not always a 2. So we'd have 21.5 divided by 30.1 times 3120 divided by 2. So our answer, rounded to 4 sig figs, would be 1,114 kilojoules of energy. So that's how we do some heat stoichiometry. If there's any questions, just let me know.